So good day, I am George Jr. P. Sardilla. So today I will be presenting to you the chapter 8, which is the Do Dice Play God. So for centuries, science was dominated by Isaac Newton's vision of a clockwork universe. A world that runs like a perfect machine. If you knew all the forces and positions of every object, then in principles you could predict the entire future. This idea was famously expressed by Pierre-Simon Laplace, who imagined an all-knowing intellect able to see past and future at once. At first glance, this seems reasonable. Newton's laws are always deterministic. The same causes always produce the same effects. But everyday experience tells a different story. Whether forecasts fail, dice rolls seem random, and even simple systems behave unpredictably. So what went wrong with Laplace's vision? The key mistake was assuming that determinism means predictability. Modern mathematics shows that this is not true. The answer: chaos theory. Chaos theory reveals that many systems follow exact deterministic laws but are still unpredictable in practice. Why? Because of sensitivity in initial conditions, often called the butterfly effect. Tiny differences in starting conditions, too small to measure, can grow rapidly and lead to widely different outcomes. A classic example is a dripping tap. At low flow rates, drop falls in a steady rhythm. Increase the flow slightly, and the pattern becomes irregular. Even random sounding, yet the system is still governed by physical laws. If we knew the initial conditions with infinite precisions, we could predict everything. But infinite precision is impossible. So, to understand such behavior, mathematicians like Henry Poincaré developed a geometric way to visualize motion using phase space. Instead of calculating exact numbers, we study shapes called attractors, which show how systems behave over time. Regular systems have simple attractors, like points or loops. Chaotic systems have strange attractors, complex, fractal shapes that reveal hidden order within apparent randomness. Chaos is not disorder. It is deterministic behavior that looks random. One of the most striking discoveries in chaos theory is a period doubling route to chaos, where systems shift from regular motion to chaos in a precise pattern. This pattern is governed by a universal constant called the Feigenbaum number, which appears in systems as diverse as dripping taps, electronic circuits, fluids, and magnets. This shows that chaos has deep, universal laws. Chaos even has practical uses. Scientists now use chaotic control to steer satellites with minimal fuel, stabilize irregular heartbeats, reduce turbulence, and improve engineering systems. Living organisms themselves rely on chaotic dynamics to respond quickly to a changing world. At the deepest level, chaos raises a profound question. Is randomness fundamental to nature? Or could even quantum uncertainty hide an underlying deterministic chaos? So, we don't know yet the answer, but chaos theory has transformed how we think about order and randomness, showing that nature's unpredictability may still be governed by elegant rules. This universe may not be a simple clock, but neither is it a pure chance.